Ladies and gentlemen, good afternoon. I'm Ji Chao, a master student from Tsinghua University. I'm very glad to have this opportunity to attend the conference. The topic I'm asked to speak on is water condensation and chocolate vacuum behavior on GDR in PMFC by molecular dynamic simulation. I'd like to divide my presentation into five parts: research background, model building and validation, pure water condensation system, water and hydrogen condensation system, and conclusion. In the first part, I'd like to talk about the background. Energy is being consumed as a necessity of life, while people are pursuing a more convenient life. The main source of energy in the world today is still fossil energy. Hydrogen energy is being considered to be one of the excellent alternatives to fossil energy because of its advantages, such as easy transportation, high calorific value, especially the doesn't cause greenhouse gas emissions. As the ecological environment continues to deteriorate, hydrogen energy is more frequently used in construction, transportation, and other fields. Particularly, hydrogen cells are widely used in the field of power generation. Proton exchange membrane fuel cells, the PMFC stands out among many fuel cells because of its low operating temperature and high power density. The page you are looking at now is a common PMFC working system. In this system, PMFC is equipped with high-pressure hydrogen storage tanks, injectors, and other equipment for hydrogen recycling to enhance the efficiency of hydrogen utilization in the system. Inside PMFC, ions combine to produce water, some of which is expelled from the gas diffusion layer, the GDL. However, when the water content is too much, the GDL will be floating, blocking the contact between the gas and the electron, resulting in insufficient cell fuel. On the other hand, if the rate of water production is less than the removal rate, PMFC will become dry, unfavorable to the movement of protons may lead to irreversible degradation of the membrane. Strengthening the water management of PMFC is significant. Existing research faces the following main obstacles. Firstly, the water content inside the PMFC is difficult to control. And secondly, there is a lack of numerical studies on the macroscopic aspects of condensation process. Therefore, based on molecular dynamic method, we simulated pure water condensation system and water hydrogen binary condensation system and studied the condensation process of water molecules under different conditions from the microscope perspective. The second part has to do with the model. The later Jason's potential energy function is used to describe the interaction between molecules. It includes a non-bonding term and a bonding term. The non-bonding term represents the interaction between different molecules or non-adjacent atoms within the molecule. The bonding term represents the interaction between chemically bonded atoms, including bonding energy, continental bonding energy, and a double-sided angle distortion potential. Lorentz first law mixing rule is used to get the related parameters for different atoms, and alpha is referred to as the interaction coefficient. The nucleation rate is a macroscopic manifestation of liquid condensation, and the classical nucleation theory was used to calculate the nucleation rate at the end of the simulation. In order to ensure the precision of the molecular model during the condensation process, the simulated values for the density of water and hydrogen were compared with the corresponding data in the National Institute of Standards and Technology database. It can be seen from the figure that they are very consistent. In addition, the self-diffusion coefficient of water was also verified, and the maximum relative error is 25.8%. Now we come to the pure water part. In the simulation, we replace the GDL with graphene. From the bottom to the bottom, the surface is divided into a fixed layer, a temperature control layer, and a thermal conductivity layer, with the fixed layer preventing the surface from moving, the temperature control layer controlling the temperature of the surface, and the thermal conductivity layer absorbing heat from water. The interaction between the carbon atoms and the water atoms changes by adjusting the solid-liquid mixing coefficient alpha. To study the effects of alpha on the condensation, we increase the alpha from 0.3 to 0.7 and observe the change of the process. As alpha continues to increase, the attraction between water molecules and the carbon molecules increases, and the water molecules are bound to the surface of graphene. As shown in the figure, condensation speeds up and eventually larger clusters form. The water contact angle can reflect the hydrophilicity of the solid surface. The smaller the water contact angle, the more hydrophilic the surface is. Here are the cases where the solid-liquid mixing coefficient alpha was 0.5, 0.6, and 0.7. After measurement, the water contact angle decreases from 100.2 degrees to 65.5 degrees. It means that as the alpha increases, the contact angle between the droplets and the graphene gradually decreases, and the graphene's ability to remove water weakens. Next, the impacts of different simulation conditions on condensation are discussed. The influence on condensation is reflected through changes in the average number of clusters in the water molecule monomers. By calculating the average cluster size, it can be equivalently assumed that each cluster is growing over time rather than gliding maturely. The growth rate of average cluster size accelerates with the decrease of cooling temperature. Similarly, the curve shows a faster growth rate with an increase in initial pressure. Monomers are the basic elements for forming clusters. The water in the system exists as individual molecules at the beginning, but nucleation progresses. Monomers combine to form polymers, resulting in a decreasing number of monomers. At lower cooling temperature and higher initial pressure, monomer consumption is faster, which results in faster cluster growth. Now we come to the water-hydrogen binary condensation system. Firstly, the formation and the evolution of clusters was studied by analyzing the maximum cluster size. The condensation process can be consisted of cluster nucleation and droplet growth. After quenching clusters nucleate at 0 to 1,500 picoseconds, fluid molecules collide and gradually generate several small clusters. The size of the largest cluster increases almost linearly. After that, the size of the largest cluster undergoes multiple jumps, indicating that cluster merging is the main process during droplet growth. In order to directly observe the condensation process, the images of maximum cluster at different times were derived, compared with 5 nanoseconds. At 2 nanoseconds and 3 nanoseconds, the distance between molecules in the maximum cluster is further and the clusters are looser, indicating that the distance between molecules decreases during the condensation process, especially at 2 nanoseconds and 3.5 nanoseconds. There is a clear boundary within the cluster, indicating that the largest cluster is the aggregation result of small clusters scattered together. In addition, we analyze the overall clustering situation of the system at different time points, and found that over time the number of small clusters decreased, while the number of largest clusters increased. The number of the cluster size corresponding to the extreme points of the curve decreases from 216 to 118, while the extreme points move toward to the direction of large clusters, indicating that small clusters are aggregating into large clusters. Similar to the pure water system, we studied the influence of different initial conditions on the condensation process. Keep initial pressure constant, increase the initial temperature would reduce the final size of the largest clusters, decrease the average cluster growth rate, and be detrimental to the condensation process. The initial pressure is adjusted by controlling the hydrogen content as the pressure increases. That is, the hydrogen content increases. The number of clusters and the number of water molecules in the clusters will both decrease, indicating that diffusion will handle the polymerization behavior of water molecules and reduce the condensation rate. Next, we compare the simulated nucleation rate with the theoretical nucleation rate. To obtain the simulated nucleation rate, we first analyze the evolution of clusters containing N or more molecules over time, change the threshold, and obtain different curves. Then synthesize the linear growth rate of these curves in the initial stage. The corrected nucleation rate is calculated based on tensor basis revised nucleation theory. For both pure water systems and the water hydrogen binary systems, the simulated nucleation rates are between the two. However, for pure water systems simulated under high pressure, the calculated nucleation rate is closer to the corrected nucleation rate. For water hydrogen binary systems simulated at room temperature and low pressure, the calculated nucleation rate is closer to the classical nucleation rates. Finally, let's move on to the conclusion. Our main work is to use molecular dynamic simulation methods to conduct microscopic analysis of the condensation process of water molecules in pure water system and water hydrogen binary system, providing theoretical basis for understanding the condensation process of water molecules at the microscopic level and controlling the liquid water content. The condensation process in two systems was studied from the aspects of solid-liquid interaction coefficient alpha, initial pressure and cooling temperature, and the depletion rate. Through this research, PMFC can select suitable materials and working conditions in the future to further improve working efficiency. This is all I have to report. Thank you for listening carefully. If you have any questions, please feel free to ask, and I will answer you to the best of my ability. So, have you answered the questions?
I don't think he's online. Let me check. No, I don't think he's online.
Okay.